A riverbank doesn't erode slowly. Often, the soil structure fractures under the current, collapsing rapidly and pulling large swaths of land into the rushing water. This is Majuli, the world's largest river island, located in the Brahmaputra River. The collapsing land here means permanent loss of structural infrastructure, forcing thousands of residents to abandon their homes as the river consumes the shoreline. This image shows the core data complication for tracking that land loss. The seasonal monsoon brings heavy flooding that temporarily inundates the landscape. From a satellite perspective, this shallow surface water looks nearly identical to permanent structural bank erosion. Traditionally, distinguishing between temporary floodwater and permanent land loss requires human analysts. They manually download multispectral raster imagery from satellites like Sentinel or Landsat, process it in GIS software, and build complex spreadsheet models to calculate mitigation needs. Because this manual processing takes significant time, disaster response teams are forced to allocate emergency resources based on outdated data, losing critical reaction hours when the riverbank is actively failing. GeoDrishti is designed to close that time gap. It is an autonomous, multi-agent conversational copilot that pulls live satellite telemetry and overlays it directly onto an interactive map. Building a tool for high-stakes disaster logistics introduces an immediate engineering problem. Large language models are inherently non-deterministic. If left unconstrained, they hallucinate facts, which is unacceptable when calculating physical emergency budgets. To make the system reliable, we have to isolate clean data at the source layer, build an agentic orchestration layer to divide the cognitive load, and clamp the language model with strict, hard-coded boundaries. Developing a trustworthy AI for disaster response requires less focus on maximizing a model's raw intelligence and heavy emphasis on engineering absolute physical constraints around its behavior. Before the AI processes any information, the system must filter the raw data. It has to isolate the permanent soil erosion from the temporary seasonal monsoon flooding. GeoDrishti queries the Google Earth engine for Sentinel-2 satellite imagery. To bypass the monsoon entirely, it strictly filters the results to extract only dry season composites captured between January and March. The system calculates the NDWI, subtracting near-infrared from green to generate a zero-threshold water mask. Comparing these year over year tracks assigned water area delta. A positive number means water expanded, erosion. A negative delta means water shrunk, natural land accretion. By restricting the temporal window and running strict mathematical filtering at the remote sensing layer, the downstream AI is fed purely structural data. Without this, the model would declare an erosion crisis every time it rained. With clean data established, the conversational core runs on Gemini 1.5 Flash. Instead of using a single monolithic prompt, the system relies on the Google Agentic Development Kit to sequence 3 specialized agents. Agent A, the GIS operator, parses plain English requests into structured coordinates. Agent B, the environmental analyst, fuses database statistics and live satellite telemetry into a risk report. Finally, Agent C, the resource planner, calculates required geobags and bamboo to generate a resource plan. Dividing the labor this way isolates language parsing, geographic data analysis, and logistical math, rather than relying on guesses. Even with specialized agents, relying on a language model for hazard assessment carries a specific risk. An LLM might classify 500 lost hectares as medium one day and high the next, purely through non-deterministic generation. GeoDrishti removes the model's authority to judge severity. Raw acreage is routed through a deterministic Python logic gate. If a loss exceeds 1,000 hectares, the string high is forcefully injected into the structural prompts of the agents, forcing exact compliance. To bridge this deterministic backend with the agent workspace, the system uses FastMZP, a model context protocol server. This exposes the database queries and Python logic gates as secure tools the agents can call. Enterprise infrastructure tools do not ask a language model to calculate risk. They require the model to format and present a risk already calculated by rigid mathematics. Multi-turn conversations introduce another vulnerability, session state leakage. This happens when variables from a previous question linger in memory and corrupt the current analysis. For example, if a user asks for an erosion report on Tokyo and then follows up with a query about Majuli, The system risks carrying global telemetry into the local mitigation plan. To block this, the system enforces explicit nulling. When a query hits an early exit, fails validation, or completes, the code returns a null state for all payload variables. The system also sanitizes inputs and applies strict bounding box checks. Any temporal query spanning more than 5 years is automatically clamped to protect the backend. Memory in an AI agent is a liability if left unmanaged. Explicit state resets guarantee that every disaster report is built entirely on its own isolated data. This architecture is deployed with a cloud-run backend, managing the SQLite database and Python logic, serving a static Firebase frontend. When a user submits a query, the leaflet map dashboard automatically flies to the resolved coordinates. It renders the historical trend graphs and populates the localized mitigation budget. Once the analysis is complete, an emergency dispatcher kicks in. It packages the raw data and the localized resource plan into an SMTP email, directly notifying the District Disaster Management Authority. Tracking the physical collapse of Majuli Island used to require days of manual raster processing and spreadsheet modeling. Now it is driven by an automated, telemetry-driven workflow that resolves in seconds. GeoDrishti proves that implementing AI for physical infrastructure requires strict control. Success relies on building precise, deterministic systems that harness the model's processing power while enforcing absolute mathematical reality.